Have you ever wondered what the difference was between your crummy old laptop and a quantum computer? Let's start by breaking down what a regular computer is made of. This is the most simple electric device, an electric switch. It can be in one of two states, either on or off. Computers like the one you have in your bedroom right now are made of thousands of tiny little switches called transistors that are operated electrically. You can imagine transistors as a really fancy light switch. To help illustrate what these switches are actually doing in the background, I'm going to make the electrons that they're controlling visible to our own naked eyes. Switches control the flow of electricity from one place to another. When the switch is on, the electrons can flow freely, like this. This is all great until you turn the switch off. Then the electrons are blocked from where they want to go and are very sad. Aww. Just kidding, they're not actually sad, but you get the idea. We can write the states of the switches with two numbers, 0 or 1. 0 would mean that the switch is turned off, allowing no electricity to flow. And 1 would mean that the switch is turned on, where electricity can pass. As we make our computers smaller, the switches also get smaller, and we start to encounter some really interesting physics, such as quantum tunneling. What's quantum tunneling? In order to start understanding quantum tunneling, we need to first understand that all quantum particles like this photon are actually just probability functions of where they possibly might be. That's right, when your math teacher told you the world is made of math, he was actually right! Now let's imagine this photon is heading towards a wall or barrier of some sort, like that inside of a switch. You'd think what would happen is like what would happen when a ball hits a wall, but actually this is a little bit more complicated than that. As it turns out, because all particles are waves, a little bit of this probability wave appears after the barrier. This essentially means that the particle can appear after the barrier, meaning it can pass straight through the barrier. Another thing to know about is particle superposition. Particle superposition is essentially what happens when you get two states of a particle at the same time. For example, the polarization of light. Have you ever seen those cool new 3D glasses they have at the movie theaters that look like sunglasses but actually aren't, and when you put them on they give you a real big headache? No? Oh, well, here's one, just as an example. Here you go. This is what it looks like. Just by looking at these sunglasses, you'll quickly notice that the two lenses look pretty similar, but in reality they're very different. The right one is polarized vertically, meaning that it only allows light pointing up and down through the lens. Similarly, the one on the left is polarized horizontally, meaning that it only allows light pointing left and right to go through the lens. But, I hear you cry, what if it's polarized at an angle? Well, you are a very smart person. You have essentially discovered what the idea of superposition is. In this case, the photon is in a superposition of both vertical polarization and horizontal polarization. It is part up and down and left and right. In a quantum computer, what we've essentially done is merge these two bits into a superposition of both 0 and 1. This bit, which takes advantage of the quantum idea of superposition, can be called a qubit. You'll usually find qubits in quantum computers that look like they came straight out of Star Trek. These machines are specially built to handle the weird physics of the quantum realm. Let's compare how numbers work on these two different types of computers. First off, we have the classical, regular old PC. My regular old PC stores the number 3 as a set of 8 bits, 00000011. This is just binary for the number 3. My crazy newfangled quantum computer can store the number 3 as 1 qubit. This qubit would have to be in a superposition that is 3% the state of 1 and 97% the state of 0. Compared to 8 bits, 1 qubit is very impressive. It allows us to store lots of information on just one particle. From here it can get very complicated, including quantum gates to replace regular computer logic gates. I'm not gonna get all into that, but now we know what quantum computers are all about.